We want to find the equation of a line P naught and a vector parallel to a given vector V. So the idea is that I give you a vector, and imagine this surface as the vector. I give you a vector, and then I give you a point, and I want to find the equation of a line that goes through that point and is parallel to this vector. Okay? Think of it as we talk about this. Think of the unit vector, or as of the normal vector. Now let me think about that. As the unit vector for a vector as the slope. The unit vector for a vector is a slope. You remember I told you, if we take a vector and find a unit vector, turn it into a unit vector, that becomes the direction of the vector. And you and I learned in Cal 1 that that's also what the slope of a line is the direction of the line. So think of that as the direction of a vector. So what we're going to want to do is we're going to want to find a line through that point in the same direction as a given vector. Doesn't this sound like the point slope equation of a line? And that's what it is. So what we do is we define a vector R naught, which is R naught is a vector, remember, that is the position vector for the given point. What is a position vector? And don't tell me you don't know, because you do. If I talked about a vector that goes with a point in standard form, what does that mean?
Unit vector?
Yeah. No, it's not a unit vector until you divide by the magnitude, right?
Was it IJK then?
What?
IJK?
Yeah, here's what I want you to say. A position vector is the vector from point. That's what the position vector is. You remember when we first started talking about vectors, we started talking about vectors from the origin, right? That's all we're talking about. That's called the position vector, Okay? And wouldn't the position vector in vector notation, wouldn't it be just that? To find that position vector, don't you subtract the beginning from the end and you got a vector? And the beginning is the origin. That's why they call it the position vector. Okay? So now what I've got is I've got a position vector for the point, and then I've got a vector for the line that it's parallel to, right? And I want to make an equation of a line that goes through it. And we're going to use parametric equations, and I'm going to say x is equal to x naught. Is that the x coordinate from the point that we know? Plus t v1, where v1 is that's the vector v. So the I am defining this line in terms of parametric equations. Didn't we do that at the very beginning of the semester? And all I'm saying is that this line through this new point is the point that we know times t, a parameter, times the vector that we're using to define the position. How about y equal mx plus b? Didn't I say that the vector v is what gives us the tilt of it? And this comes directly from the point that we know. And we also know that there's more than one vector that is parallel to this line. There's the one right there, but there's also one right there, isn't there? So there is a family of them, right? And isn't that what the t means? The parameter governs which one of the family of vectors that we're talking about. Okay? I'm trying to get you to feel a little bit more easy with this because it appeals to what we know about lines in 2 dimensions, right? And then once I tell you that, I don't even have to write the other two, do I? You know what's coming next, don't you? And you have defined the line. And if you wanted to bad enough, you could get rid of those parameters, could you not? What if you told me to get rid of the parameters, I'd solve for t and say this equation, and then I'd just keep substituting and eventually get rid of the parameters. Okay? So, time for an example. Page 707. And this is parametric equations of a line through. There it is. Here's what I want. I want to find the line through this point that is on a vector parallel to this vector. And that does indeed look parallel to it, huh? Okay? So, it's really easy enough, isn't it? This is our x naught, y naught, and z naught. And there is v1, v2, and v3, huh? And from there on, it's y equal mx plus b, right? So, x is equal to x naught, which is the point we know, plus a whole bunch of vectors, a family of vectors, times the x component, 2. And some people put the 2 in front of the t. And y is equal to 4t, and z is equal to 4 minus 2t. Questions? Everybody? Y equal mx plus b. And the x in a straight line is that which varies, and isn't that the t in a parametric equation? Questions? Questions? Now what I want you to notice is, what they did is, they substituted 0 for t. When t equals 0, don't you get the very point that you started with? Is that right? You have to, don't you, by the way we set it up. But then what they're showing you is that if you let t equal 1, you go to this point by just substituting in, right? And by t equal 2, you go to that point. And they plotted all 3 points for you so they could show you that they are indeed on a vector parallel to the given vector. Pretty slick, isn't it? And just an extension of what we've been doing a long time. Questions, anybody? And I'll put one like that on the test, and you ought to be glad. That's somewhat better than a limit comparison test on an infinite series, huh? Next is, I never understood next, to be honest with you. Says parameterize the line segment joining the 2 points. That's what we just did. That's what we just did, is we found a line segment joining 2 points. We find, don't we find the vector between those 2 points, and that's V? And then we do what we just did, and not surprisingly, we get the same thing. I think we'll skip that one. Next. What I told you before, I want you to write these down or memorize them. I want you to remember that cosine theta is equal to the dot product over the magnitude of each. And sine theta is equal to the cross product over the magnitude of each. It would serve you well to remember those. What do you think each means? Each what? Vector. Each vector. In order to have an angle theta in the first place, don't we have to have 2 what? 2 vectors that intersect, right? And isn't that angle the vector, the angle between the 2? So each ought not to trouble you if you're talking about an angle, because you know exactly what each means, right? The 2 vectors. If you'll remember that, it'll help you a lot. In fact, how many of you know Patrick McDonald? He's one of our engineering majors and a very good student, works hard and enjoys what he's doing. He's figured it out. That you can do a whole lot with trigonometry, and the more engineering courses the more you take, the more you'll be drawing little triangles all over the place, right? And with those triangles, you sometimes have sine theta or cosine theta as part of the triangle. For example, suppose I have this point in space, and suppose I have this line in space, and suppose I want to know the distance of that point from the line. If this is PS, where S is known, I want to know that. But if I were to call this U and this V, vectors U and V, and V's going to have to be given, isn't it? Because I want to know the distance from that point to a given line or vector, So V's going to have to be given. Can you compute U? You can if you know this point, can't you? So here's what you would do. You would find a point along this vector V, right? Find a point and then just draw this line and then find the components of the vector, which is a matter of subtracting the components, is it not? You follow? Which means that you could know, the magnitude of U, the magnitude of U. Once you find the vector, can't you find the length of the vector? And here, you can't do much about that, about this length, but you can that one, huh? But yet, if you knew, if you can figure out a way to find that angle theta, if you can figure out a way to find that angle theta, which by the way you can, then isn't this side, isn't this side W? That'd be the magnitude of W, and that's what we're looking for, right? But wouldn't you agree that the sine of theta is equal to the magnitude of W over the magnitude of U? Opposite over the adjacent? Everybody agree? So then, wouldn't this unknown magnitude of W, which is exactly what we're looking for, isn't that the distance from the point to the vector, is equal to the magnitude of U times sine theta? Is it not? Is that pretty slick? So do you see what I mean by getting friendly with cosine theta and sine theta? Because it's going to keep coming up. Doctors Freelow and Snyder are going to throw that around for the rest of your career here, and wherever you go, they're going to use them because, Beth, am I right, engineers love to draw triangles to take a force up here and find an effective force way down here with about 4 triangles in the middle. Is that about right? So you're going to be doing this from here on, but do you get the idea? Okay? Now there's one thing you have to remember. When you talk about, well, you don't need that right now. I'm not going to swing after the bells, right? So what we want is we want that distance, and that distance on this triangle let's see if I can do it. Sine theta is equal to U cross V, right? And the magnitude of U cross V over the magnitude of U times the magnitude of V. Is that right? But we know that distance now, by the Snyder-Freelow method of drawing triangles in space, is equal to the magnitude of U times sine theta. Agreed? But look what happens. The magnitude of U is that times the magnitude of U cross V over magnitude of U times magnitude of V. By the way, what kind of animal is this, 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 and this? Did y'all see me point? all four of these. This, 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 and this. What kind of animal is that?
Okay, son.
They're all numbers.
They're numbers. I want you, are they numbers or vectors? Doesn't the goalpost make them numbers? This indeed is a vector, but the goalposts make it a length of that vector, right? Which is a number, huh? Okay? But since they are just numbers, and this is the distance we want. You got it? Anybody in here have me for trig? In trig, I try to cut down on the number of formulas that people have to memorize. Number one, I let them use a card like I do you. But I don't know, but I don't keep but maybe a dozen trig formulas stored up there, because I can get to the rest of them with a little bit of figuring, huh? William, what does Freelo tell you in circuits about formulas?
I don't recall.
Anybody else had circuits with Dr. Freelo? Freelo says that in circuits you only have to know two formulas anyhow, that everything else comes from those two. Oh, you're a double E, aren't you? Is that right, Beth? And that's sort of the way it is with me, is that I just keep the ones that I have to find the rest of them. And what I'm telling you is when I started that problem, I had forgotten the formula for the distance between a point and the vector. I'd not forgotten it completely because I looked at it last night. But when I looked at it last night, I didn't have a clue, but I took the back of an envelope and did what I just did, and I said, I know it now. But do you see that's the difference between this stuff making sense to you and memorizing it? If it makes sense to you, you can do what I did. And that is, I ran hospitals for 22 years, and then came back to teach. And when you run hospitals, you don't use a whole lot of differential equations and techniques of integration. So you talk about rusty. I was rusty, but it came back to me. And why did it come back to me? It came back to me because it made sense in the first place. And once that happens, you never lose it. And that's why somebody like Dr. Freelo, who's doing a whole bunch of things in a lot of different areas, including teaching math for us, can bounce from one to the other because it makes sense to him. And that should be your goal. If it's not your goal, you got a tough road to hoe in engineering. Okay. So, from here on, don't we just plug in the numbers? The one thing I forgot to tell you is, and I didn't really forget to tell you, U is the vector from the given point to any point on What I'm telling you is this. I didn't draw this exactly right. What I should have done is I should have drawn the vector v and the point S, and then I should have said we need to find some p, any p along this vector, any point on that vector. How would you do that? How would you do that? How would you find a point on that vector? You find a point that would satisfy that vector equation, right? So let's do a problem. This is example 6 on page 709. An equation of the, find the, equation, I want to do 5 on 708 first. I want to find the distance from S, now from a point big S, I want to find the distance from that one. And I need some, and that L stands for line, but a line is a vector, right? Except the vector has a starting point, right? And if we don't have any other starting point, we use the origin as our starting point, right? So aren't we saying that we could make that a line and vector, we can go back and forth, huh? Okay. So don't I need a point P? Don't I need a point P? I've got S, huh? We need any suggestions? Any suggestions? A little bit slow on the suggestion part, guys. This one's an obvious one. Travis? There you go. Thank you, Travis. Let T be equal to any number. Isn't that how, now let's see, your high school geometry teacher told you that a line's made up of a whole bunch of points, right? And the way, if I have y equal mx plus b, the way you have a whole bunch of points is let x be a whole bunch of different numbers and find a whole bunch of y's and put them together and you got a whole bunch of points. But can't we get a whole bunch of points by letting t be equal to a whole bunch of values? But we don't need a whole bunch, we just need one. So we just pick a value for t. Remembering math teachers are what? Lazy. So what's the easiest t to substitute in? 0. So why don't we do 0? So I'm going to be brazen enough to suggest to you that P equal to 1, 3, 0 is on L. Would you think that's true? And it could be any value, right? Do you agree? So now I need the vector PS. Is that a problem? Isn't that vector 0I minus, no, plus 2 J minus 5K. Does that look that way to you? So now, aren't we back to, so then U is equal to this. Nope. And V is equal to what? What's V equal to?
Would it be the constants in front of T?
Yeah, exactly. V is equal to I minus J plus 2K. So now can I find U cross V? Yes or no? Sure, I got U and V. Why do I need U cross V? Because that's the numerator of the distance, right? So U cross V is equal to I, J, and K, and 0, 2, minus 5, and 1, minus 1, 2. And that's equal to let's see, that's equal to 4 plus 5I. And that's equal to 0, 0 plus 5J. And minus 2, well, I'll put the 0. And 0 minus 2, okay. Agreed? Could I save myself some work if I had expanded it along this column? I would have just had to do I and 1, wouldn't I? I could have skipped the middle step there altogether. And you remember on Friday I did that, huh? What'd I do, Travis? Do something wrong?
Your J, your second number there. Is
Yeah.
it supposed to be a -5 or not?
It's -5, isn't it?
Okay, I see what you're saying. Is all of minus in there? So
But then there's I tell you what, William. There's a minus right there.
okay.
The +5 comes from a -5, right? Everybody agree? But you remember on Friday the plus minus matrix I put on the board? I forgot that, didn't I? So is this equal to 9I minus 2K? Is that right? Is this then the square root of 81?
Is your I value correct?
I don't know.
We think it's supposed to be 4 minus 5.
You're right. It's supposed to be a negative, isn't it? Let's see if that's so. I times 4, and then -1 minus 5 is 5, huh? Mm-hmm. But I subtract that product, right? So that's 3 negatives, isn't it? This negative, and the negative because it's it's the right side diagonal is what I used to call it. Agree, William?
Mm-hmm.
Okay. Okay. So now I have this.
You also need a -5J.
No, I think you got it right. -5. It's a negative. Then it's minus a negative.
I
It's
think,
positive.
yeah, I think right here is where I had it. I may have done it again here, but I don't think so. I think right here I did -5, which is in the front.
I think what he was saying was in the second step, you omitted the J.
Shall we start this over? This is I times 4 minus 5. That's right. The J is a minus in front, and then this minus this, right?
Nope. You're using J's column.
Ah, that's it. It is 0. It is 0 minus a -5. Okay, I think that's right.
But wouldn't you still have a J after when you have the equals I -2K? Wouldn't a J go down there too?
Yeah, yeah. Why in the world did I leave J out? Thank you. Because I guess I was in a hurry.
I know we're interrupted a lot, but one more. Where's the sign on the I? Shouldn't it be a negative for that one? The last step.
Right here,
Yes, sir.
is that what? Last time I checked. But other than all of those, I did it right. -1 squared is 1. 5 squared is 25. 2 squared is 4, huh? So is that square root of 30? Okay, Now I need the magnitude of u, don't I? I need the magnitude of u. And that ought to be the square root of, and u is 4 plus 25. Is that right?
I thought we were dividing by the magnitude of V.
Do what then?
I thought we were dividing by the magnitude of V.
All I was doing, yeah, I didn't need u, I needed v, huh? The u's divided out. Okay. But in case you wanted to know what the magnitude of u was, I thought William would want to know, so that's why I did it. That's the square root of 1 plus 1 plus 4, which is equal to the square root of 6. So now the distance that we're looking for is the square root of 30 over the square root of 6, which is equal to the square root of 30 over 6, which is the square root of 5. And we really didn't do anything except just sort of what made sense to do, right? I needed a vertex at a point P, so I found a point P, didn't I? And once I found a point P, I knew I had a right triangle because the distance from the point itself to the vector or the line that was given to us, that distance is at a right angle, isn't it? So then I just went back to trigonometry. Question? Okay? What does it take to define a plane?
3 points.
What?
3 points.
3 points defines a plane, huh? 3 points is 2 lines. Do you agree? So if you make 2 lines, right? Then you take the cross product of those 2 lines and you find a vector, don't you? What kind of vector? You remember what I told you Friday about names for this kind of vector? There are 3 of them. One of them is, one of the names is a perpendicular vector. Isn't the cross product of 2 vectors a vector that is perpendicular to the plane that contains those 2 vectors? And I told you there were 2 more words, and we're going to use the normal is what we're going to use. The other one is orthogonal, and you'll see that in linear algebra, and it'll come up in differential equations too, or orthogonal. But orthogonal, perpendicular, and normal. But in vectors, we call it a normal vector to a plane, because remember that trowel I was telling you about? That's the grip, huh? Mm-hmm. That's the grip on that trowel, I think it's strange to this day that we use a vector that's not on the plane to define the plane. So we need 1 point and a normal vector. Agreed? Or we need, as William pointed out, 3 points on the plane, in which case we'll use any one of those 3 points and the normal vector. Or we need 2 lines or 2 vectors on the plane, in which case we'll just immediately find that normal vector and a point on that plane somewhere. Okay? So, I think that a plane is equal to, first let me do a little bit of defining. P is any point on a plane, and it is a point, isn't a point in space determined by 3 coordinates, x, y, and z. So a point on a given plane would have to have x, y, and z in it also, right? And suppose I know a point P naught That's one definition of a plane. And that is, if I know n, what's n always going to mean? The normal vector, huh? I don't care how you got that normal vector. I don't care if I gave it to you, if you found it yourself, if you used another problem to get. Somehow, miraculously, you found that normal vector, huh? So if you know the normal vector and the point, then you do the dot product of the two. Question? Question? Oh, by the way, the dot product is a what?
Scalar.
A what?
Scalar.
Scalar, a number, huh? Is a number. But I'm telling you, this P naught P is going to have X, Y, and Z in it, is it not? Is it not? So what you're going to have is it's going to be a number, but it's going to be a left side with X, Y, and Z in it, and a right side equal a constant. And that's going to be the definition of the plane. Okay? I won't do that. Don't write that down yet. If that normal vector has vector components A, B, and C, and if you take and P naught P, is it P naught P? Isn't that the way you form a vector between 2 points that you know? Does everybody agree? So now when I do the dot product, isn't the dot product first times first, second times second, third times third? And isn't that what I've just done? So, or no. Look what I did. Isn't all I did was I distributed this A, B, and C, and wouldn't I have AX minus AX naught, and similarly all the way through? So I left the X's on this side, and then when I moved all those others to the other side, they get to be positive. And now I have AX, BY, CZ added together is equal to some number. And that is the definition, that is the equation for a plane. This equation, or this equation, all define a plane. Everybody okay with that? And we didn't, and what's A, B, and C? Big A, big B, and big C? Where do they come from?
Normal.
The normal vector. So do you see how easy this is? It is, you just pick these right off the normal vector, right? And then what you do is you do the given point. You do the given point on the plane, and you multiply it by the normal vector scalar and add them together. So you need a point on a plane. That a point on the plane is the X naught, Y naught, and Z naught. And you need a normal vector. And there are a bunch of ways to get that normal vector. The one that will happen least frequently will be the one where I say, here's the normal vector. You'll have to do something to find it, but that's no big deal either. That's a cross product, isn't it? Questions? I hope this makes sense to you, and I hope you'll try to remember all of this instead of just treating vectors as foreign bodies and plugging numbers into formulas. Okay? See if I can't find it better. This is example 7 on page 710. Well, at least they made it easy for us. I know 3 points on a plane. I know 3 points on a plane. And now I want to find the equation of the plane. So are we not going to use, and you agree, a plane is formed by either 3 points or 2 lines, right? So aren't we going to use those 3 points to make 2 vectors on there? So, shall we? And does it matter? I think I'll find, I'll let the vector u be equal to the vector av, which I think is equal to 2 minus 0i plus 0j plus 0 minus 1k. Do you think that? Which is 2i minus k. And then I'll let the vector b be equal to the line OAC. And AC doesn't really matter, does it? But AC is equal to 0i plus 3k minus k. Or 3j minus k. Okay? Now, let's see. I've got all kinds of points, don't I? I need a normal vector, don't I? So, I'm going to do u cross v, and that's equal to I, j, and k, and 2, 0, minus 1, and 0, 3, minus 1. And I think that's equal to 3i. That is 0 minus a minus 3, which is plus 3, and then 0 times 6 only. That's minus, with a minus in front, is 6j. And then k is equal to plus 0 plus k is 6 minus 0 with a plus in front, plus 6k. Look right to you?
The G term.
Well, let's see. K is 6 minus, that's right. J is minus 2, right?
Right.
Minus 2 is the coefficient of J. Only it's minus 2 times a minus, right? Which is plus 2. And then I is minus a minus 3. That looks right to me. Okay? And then I need the magnitude of U cross V, which is equal to the square root of 9 plus 4 plus 36, which is equal to the square root of 49, which is 7. And then I need the magnitude of V, which is equal to the square root of 3, oh my goodness, they're being nice to us. 3 plus 1, which is equal to the square root of 4. I don't know, is it too good to be true, Ed?
Well, I should have square root of 9 plus 1.
9 plus 1.
It is, yeah. So saying if it's too good to be true, it's probably not. Which is equal to the square root of 10. So then, I didn't need that anyhow, did I? I found the normal vector, didn't I? William, did you ask me to find that? Okay, so now the plane is 3x plus 2y plus 6k, 6z, right? Isn't that the last one I used a minute ago? And that's equal to, and shall we use A? So that was V1 A1 plus V2 A2 plus V3 A3. Isn't that what that constant was? Is that right? Where this is A1, A2, and A3. And this, and the V's, V1, V2, and V3. Isn't that the way we did it? So, is that equal to 0 plus 0 plus minus 1 times 1? So isn't the plane 3x plus 2y plus 6z is equal to 1?
Negative 1?
What?
Negative 1?
Oh, Ed.
So 1 times negative 1.
Yeah. Thank you. How about that? That's not so bad, is it?
The computer says it's equal to 6.
The book says it's
book-
equal to
yeah,
6?
Sorry. Yeah, the book does.
The book says the right side is equal to 6. Well, let's see. I took the normal vector. I hope I took the normal vector. And I used the point A, huh? And it is. You know what I did? I just looked at the wrong place. I was going down the vector V when I picked off those coefficients. And I could have helped us if I'd have said that this was equal to n. Couldn't I have helped us some if I'd have just done that? Okay. So now, if A is 0, 0, 1, then doesn't that mean that the only one matters is 1 times 6? Is that right? And so there's no doubt to emphasize that that comes from the normal vector, huh? Any questions?
It's easy enough to check the work, just plug the points in there and they have to satisfy that.
Yes. 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 Did you hear what Dr. Thomas said? Substitute the points in and make sure it works. Substitute any one or all three to be safe. And on a test, why wouldn't you want to be safe? Okay? Again, we're getting to where we can find more and more and more, but we're just doing what makes sense to find it. Okay? Now I want to find, this is example 9 on page 710. I'm going to give you, I've got two planes. I got those two planes. Two planes intersect at a what? A line. Two lines intersect at a point, two planes intersect at a line, right? But if I'm looking for a line, don't I need to know need to know a point on the line? Is that right? And the slope of the line? And slope in vectors is a unit vector, is it not? Everybody agree? So, suppose we find a point on that line, on a point on the line where they intersect. Any suggestions? from this side of the room over. I want to find a point where those two lines intersect. Don't tell them, don't help them.
I'm not sure I'm gonna lie.
Would you find the scalar you multiply the functions by to get the same enters or result, so you can set them equal? So it'd be the second equation times 3, and I set the 2 equal.
Very good. I do it a little bit easier, but you just told me what to do. Let's see, if I want a point on a line where they intersect, doesn't that mean that that point has to be on both of those planes? Is that right? Everybody agree with that? So, but here's the rub. I've got two equations, and my point is going to have 3 components. And to solve those planes simultaneously, I need 2 and 2, don't I? So what I'm going to do is, I'll fix that. I'm looking for any point. Do you agree? Any point? Everybody agrees? So I'm going to say, I'm going to let z be equal to 0 for both. So now I have 3x minus 6y is equal to 15, or x minus 3y is equal to 5. Do you agree? Everybody? I'll let z out of the air. I'll let z equal to 0. Okay, I'm going to do the same thing on this one. And that is,
X minus
did I do it wrong? Did I mess that up?
No, you did one line, you're doing the first equation, dividing everything by, no.
X minus 2y.
Minus 2y equals,
Well, yes. Okay, now I have 2x plus y is equal to 5. And isn't that what happened when I let z equal 0? Does that make you uncomfortable that I just snatch that baby out of there? What in space, what is the plane z equals 0?
Origin?
No, a plane. The origin's a point.
The XY plane.
Exactly. The plane, that plane is the XY axis, is it not? And for any line in space, isn't it at some point going to have to cross the XY axis? That's why I could do it. I know that this line where 2 planes intersect has to cross the XY axis. So I just said, fine, I'll let z equal 0 and make it cross the XY axis. And am I not going to find a point on the XY axis, on that plane, where this line intersects the XY axis plane? That's all I did when I let z be equal to 0. Could I have let x be equal to 0? Yes, I could, because by the same token, doesn't it have to cross the YZ axis also? I just picked one of them and let it be 0 because I knew it was gonna cross one of those axis planes.
And that's never gonna affect what it's equal to? That's what I don't.
Well, now you know what's next. I'm gonna find, X and Y value that goes with Z equals 0, right?
Okay.
And if I'd have let X be equal to 0, I would have found a Y and Z value that went with X equals 0. Would that affect, would that affect the line? No. But would it affect what the equation of the line looks like? Which is why Cal 3 tests are such a pain. Okay? So now I take 1 and 2, you know the drill. Only I'm going to use substitution. I'm going to say that X is equal to 2y plus 5, and I'm going to call that 3, and I'm going to substitute 3 into 2. So I have 2 times 2y plus 5 plus y equals 5, or that's 4y plus 1 is 5y plus 10 is equal to 5. 5y is equal to minus 5. Y is equal to minus 1. And then I'm going to substitute y equal minus 1 into 3. And that means that X is equal to 2 times minus 1 plus 5, which is 3. So now I know what? What does that give me?
Point.
That gives me a point, doesn't it? The point P of 3 minus 1, 3 minus 1, 0, is on L, which is the line of intersection. Now I need the slope of L. Anybody want to help me with the slope of L?
Delta Y over delta X, keeping it Z 0, right?
I think that, I hope I get this on there. Oh, I do, 710.